Hello class, this is your instructor Dr. Mayas, and welcome back to our pre-recorded series of the dynamics. Today sections concerns section 12.4 and 12.5, which is the curvilinear motion. Now curvilinear motion is 2 and 3 dimensional motion of particles. Previously we discussed the rectangular or a rectilinear motion of particles, which is only described by one dimension. So, objective, describe the general curvilinear motion of a particle. Use the rectangular components, which is the Cartesian component, x, y, and z, to describe the kinematics of a particle in vector space. And we'll take a couple of examples. Alright, so the rectilinear motion describes a particle moving in one direction. In the curvilinear motion, we describe the particle moving in either 2D or in 3D. So we can say, well, I have a particle, and this particle its motion is described in y and x coordinate. This is 2D, and it follows a path. Right, this is the particle. Or we could say that this curvilinear motion is a part of a space or three-dimensional movement of an object, where we can describe x and z and y. These are all positive direction, and it exhibits, in general motion. Now, definitely we always describe the motion of this object in reference to origin. So the origin is the intersection of the axes, x, y in 2D and in 3D, x, y, and z axis. Some application of the curvilinear motion, the path of plane traced on the sky, it's a 3D. A roller coaster that is undergoing helical motion from a fixed point, say base of that helical coaster, and that is described also in 3D. Sometimes we can describe the 3D motion in a simplified 2D. So most of the examples focused here in dynamics will be two-dimensional, knowing that the 3D is can be handled in a similar way. Let's begin describing the theory. Say we have a particle, P, following a path, S, and this particle is measured from an origin, O. The position of this particle relative to the origin, O, is described by a vector, R. I'm going to always put a vector indication on the top of the symbol to say it's a vector. In the textbook you will see it bold color. So if this is a 2D, then the vector has two components, x and y, assuming that we are using the Cartesian coordinate. If it's in 3D and we are using Cartesian coordinate, then we can describe this into x, y, and z. So what is it? So consider Cartesian coordinate, which we call also the rectangular component. Rectangular components. Now this means that the location of this Cartesian y and x is originated at O and has unit vector y and x. Now how can we describe P with respect to O? We said it's R. So the R vector, which is a function of time because the particle position changes with time, is equal to what? To the component, the x t I component plus y of t j component, and if it's a 3D, then z of t k, where I, j, and k are unit vector indicating that the direction in the x direction, I, direction, the y of t is the component of the r of t in the y direction, which is called j, and z if we have a third component. Now let's say that our particle moved from a position p to p prime, where the vector r changed from r to r prime. R prime is not derivative, just saying it moved to a new location. Okay, so the displacement delta r, which is measures delta r, which is the equal to the new location as a vector minus the previous location as a vector, is indicated from p to p prime. Okay, now as delta r becomes smaller and smaller, then what do we have? We have the following. I'm going to draw another one. So as this delta r becomes smaller and smaller, this is delta r, right? Which become a derivative, then we can say delta r is equal to dr, derivative, right? And this become tangent to the path, tangent. So what does it mean? This is a tangent. So the object is moving at this instant location tangent to the curve, tangent to the curve. So the movement is tangent to the curve and describes the direction of movement or the rate of change, right? So this is very important, because what we then can do, if this delta r generated by a small time change delta t, then I can define my velocity. Velocity, the instantaneous velocity, as we know, velocity instantaneous is equal dr over dt. So therefore, if I divide this over dt, that's going to give me the velocity, instantaneous velocity. So always the velocity is tangent to the curve, not any curve, tangent to the path. Tangent, the instantaneous velocity is always tangent to the path. Alright, so what we arrive at is giving a path, measuring the motion of this, and this is the path, or sometimes we call it S curve, and let's say this is our x and y selected, and that's the vector r. Then that's going to be our velocity, tangent velocity. We said previously that the r in general, which is a function of time, equal to the component and then knowing that the velocity, instantaneous velocity, is the derivative of that, then we can introduce the derivative into each component. I plus j plus k, and all of them as a function of time. Great. Now we have done a major step here. Now let's try to plot the v as a curve. Assume that we have obtained this function as a curve, and we're going to call this curve a hodograph. So this is the velocity, or the instantaneous velocity profile, and it's called hodograph. hodograph, which is the velocity profile. This is the velocity profile, right? And then this become the velocity at this instant t. In a similar fashion, taking the derivative of the velocity is going to generate you an acceleration, right? It's going to generate you an acceleration. So let's say I have, and we know the relation between the acceleration and velocity is the derivative. So that's going to give us dx of t over dt, second derivative in I plus second derivative in y plus second derivative in z. Okay. All right. Now, I failed to mention that you can describe this in much simpler fashion, and and also as well as this. So, in summary, v can be described by its component, which is vx, this is for simplicity, as a function of time in I, plus vy j plus vz k, all of them as a function of time, which correspond to these values. As well as we can say a, acceleration, equal to ax as a function of time, I, plus ay as a function of time, j plus az as a function of time, k. Right? Where az corresponds to that, ay corresponding to this. Also, there's a notation, simplified notation that describes the derivatives, which is instead of writing dx over dt, you'll find most of the time we're writing x dot, referring to a derivative. Or similarly, dy over dt y dot, and dz over dt, you can write it as z dot. Second derivative, you can write it as x double dot. This is a simplified notation. So instead of always writing, this long dy over dt, so this is just a simpler way. Ez double dot, right? So you can always, use whatever you feel like. Now in the hodograph, we know that the acceleration is tangent to the hodograph, but typically we don't describe the motion of a particle using the velocity profile. Mostly we use the path curve, which is describe the position, which means the following, right? So if I have a particle that its path, the s path or the position path, is known, we know this is r vector, we know that the velocity always tangent, but not necessarily the acceleration. Acceleration, yes, is tangent, but it's tangent to the hodograph or velocity profile. So this could be general, could be like that, the acceleration, not necessarily tangent. There are special cases when it's tangent that we will discuss later, but this is general. So when we deal with the path or the motion of a particle along a position path, we know the velocity is always tangent to the curve. A is a vector somewhere, right? Also, we should not forget that the definition that we obtained for the acceleration and also for the velocity is for the instantaneous, right? Instantaneous, and that's equal to dv over dt, right? Or equal to dr over dt as a vector, right? Now things, if delta, if the rate of change on time is big, then we talk about the average, right? So the average is when delta t is greater than delta t, like not small time, and then we can say v average equal to r prime minus r over delta t, and these are also vectors, and the average velocity or acceleration is equal to velocity prime after velocity before over delta t, right? Delta t. So that's, you know, given and known. I think don't need to reiterate that. Let's talk about a couple of notes I would like to remind you. First, the definition of the magnitude and unit vector, and also the chain rule. So let's start with the magnitude and direction. Let's consider, and this is first from static. Those who took class with me last semester in the static, remember that the vector analysis is an integral part of almost every engineering class. So consider a vector, a position vector, r of t, which we describe it by its component in Cartesian coordinate system, right? So now we are familiar with this. Now this is a vector in space. The magnitude of r of t is equal to square plus yt square plus zt square. The unit vector, which is, call it ur, and this is a vector, equal to. Now the magnitude of this is in fact sometimes written as in that form, sometimes without this r, so I'm always gonna write it as a norm. This is called norm. Is equal to the magnitude or the norm multiplied by r of t. So it's called unit vector because the magnitude of this is 1. So we can take some example in future and see what that means. This same applies for the velocity, applies for the acceleration. So similarly, acceleration and velocity, same fashion. I'm not gonna write it again. Another important note I would like to mention here is the chain rule. Chain rule, or the change and the variable. Suppose that we are given a function, call it f of x. Given a function f of x, right? This function, if we were asked to derive this function with respect to time, then the derivative of this function, which is function of x with respect to time, it can be written also as a derivative of this function with respect to its variable multiplied by the derivative of the variable with respect to time. And again, if you want to think of it, look at that this way. So it's look like df of x over dt, and this is the same. So I haven't really done much. This is going to help us a lot. Let me give you an example. I will find this very useful. Consider a function equal to x squared plus 1, and this described the path of a particle. And also consider that we are given the velocity of this particle in the x direction, 2 meters per second, let's say, right? And I'm asking you find the velocity of this particle in the y, right? So how are you gonna find that? Well, it's simple. You're gonna say, well, I'm giving f of x equal to or I'm gonna take the derivative of f of x with respect to time, and that's gonna be equal to derivative of f of x over dx over dt, where f of x equal y, right? So suppose this is equal to y. Great. So this means dy over dt is equal d over dt of x squared plus 1 and equal d over dx x squared plus 1 dx over dt, right? And that's equal to 2x, right, multiplied by, this is already given to us, by 2, equal to 4x, right? Great. Okay, let's take this example. We have a particle moving along a path y equal to 0.5 x squared. This particle starts from a rest position, and it's start from the origin, mean at a time equal to 0, x and y and z equal to 0. Also given to us that the velocity component in x direction is given and equal to 5t feet per second. We want to find the distance traveled at time equal to 1, and also want to find the magnitude of the acceleration at time equal to 1. This is the magnitude of the acceleration. And so for the first part, the distance traveled, it means simply find the norm of the position vector. So we need to find the norm of position vector where r is equal x of t I plus y of t j evaluated at time equal to 1, right? For the second part, this is just brainstorming with you. The magnitude means find this norm, right? ax plus ay square, right? Where ax, or in general a as a vector equal axi plus ayj, because we're dealing with only two dimensions. The steps. Okay, now to determine the x and ax, we need to integrate and differentiate the velocity component using the initial condition. So we can go back. So given that dx over dt equal to 5t, and giving that the initial condition is 0, I can rearrange this and say, well, this is equal to 5t dt, integrate at time equal to 0 from initial condition, this is was 0, how much it will displace in x component at 1 second, right? So this is integration of 1 is x from 0 to xf equal to 5 over 2 t squared from 0 to 1, and that's gonna be equal upon substitution. This is equal to 5t and 1 minus 0. Therefore the displacement, let's say call this displacement in x within from 0 to 1 second is, I'm gonna write it this way, from 0 to 1 second is simply 5 over 2 feet. Okay, so we need this because to find the distance we need the norm. Now we have so this, in fact, this is equal to x squared plus y squared evaluated at time equal to 1. So we already have this one, right? Or this is the distance traveled, right? I'll call it distance traveled. Alright, so let's see what we can do with the acceleration. So given v, which is given to us, which is dx over dt, then dv over d time is equal the derivative of this 5t, which is equal to 5 feet per second square. So it doesn't change really regardless of the time, so it's a constant. So this defines ax, right? So ax at time equal to 1, right? It's equal to 5 feet per second. Now what's missing from all of that is we want to find the component in y, right? The component in y. So this is where the chain rule applies. Just to recap, we want to find this and we want to find that. This is the distance and that is the magnitude. And what we did so far, we found the displacement. We said that this displacement from 0 to 1 second, we found it to be 5 over 2, and also for the acceleration we found ax, and that was a constant, right? So this is in feet and this is in feet per second square. Now we want to evaluate what? The y from 0 to 1 and also the ay component. Okay, now for the first one we're given that y is already known as a function of x, 0.5x, so how much is y will displace when x equal to 5 over 2? Just simple substitution. So y at time equal to 1 is equal to 0.5, right? At time equal to x equal to 1, which we already know it, and this is 5 over 2, right? Square, and that's gonna be 3.25 feet. So immediately I can now calculate my displacement, and my displacement will be what? 2.5 square plus 3.125 square, and that's gonna be 4 feet. So we already solved the first problem. Now for the second one I need to find ay. How to find ay? Great. Now given y equal to 0.5x squared, I can do the chain rule. So dy over dt, which we really don't know, that can be written as dy over dx, dx over dt. We know this, we can calculate that, and that is equal to dy over dx is simply 0.5 multiplied by 2 multiplied by x of t, dx over dt, which we already know it, and it was given to us as a v of x equal to 5 of t. So that's what's given to us. Now if we want to evaluate the displacement in y at this time, I need to know the value. I can substitute 1 here, and I can substitute the value of the position in x at 1, which we already know it. We calculated that already, right? So how is it, and how much is it? This is simply is as follows. So this is going to be equal to 0.52 by 22.5, which is the value of the displacement in x at time equal to 1 by 5 by 1. But anyway, this is not really, we don't need it, although in the previous example I showed you how to calculate the component, but that's, you know, an extra. This is extra knowledge, right? But anyway, going back to our goal is how to find ay. So now given, so what did we get from all of that? We got that dy over dt is equal, this is the one, equal to simply 0.5 by 2 is 1 x of t, and this is, it was dx over dt, which is x dot. Okay, so this is dy over dt. Now if I want to find ay, which is second derivative respect to time, which is going to be the derivative of this with respect to time. What does that equal to? So I'm going to need to apply the derivation rule. This is equal to, well, I'm going to say d over dt x of t, x dot of t plus, right, plus I fix this d over dt x dot, and this is x dot with respect to time. So what is it? This is x dot plus x, and this is x double dot, right? This is equal to y double dot. Okay, so continuing, now that's it. I need just to know what x dot, and so this is x dot square. X dot square is already given to us as 5t, so this is 5t square plus and this is x of t, which is evaluated at time equal to 1. This is should be evaluated as time equal to 1, and x double dot is the second derivative of the position. So just let's be much more organized here. So this is x at a time, and this is x double dot at a time. This is 5t just square plus x of time. X double dot of t is 5, right? Now I need to evaluate this at time equal to 1. So y double dot at time equal to 1, this is 5 square plus x of 1 multiplied by 5. X of 1 is, we found it to be 2.5, which is so we have a 25 plus 2.5 multiplied by 5, and that's going to be equal to 37.5 feet per second. So finally, and allow me to use this corner, so the norm equal to what? It's going to be equal to the ax squared plus ay square, and that is ax square we already found is 5 square plus ay square. This is what we just found here, 37.5 square, and that's going to be 37.8 feet per second square. So that's the magnitude of the acceleration. So with this, we conclude today's lecture. You are welcome to go back to the presentation file and see the solution more in detail. There's some attention quiz. So the most thing we needed from this lecture, I think we captured it. So good luck. If you have any question, let me know. Next lecture we meet.